Start by understanding what a network really is. Imagine a group of computers and devices all connected together so they can exchange data. Each device or node on this network has a unique address, usually a numeric one like 204.160.241.98. While these numbers are easy for computers to handle, they're not so friendly for humans. That's why networks often provide names like www.javasoft.com, which are much easier for us to remember. These names are mapped to numeric addresses behind the scenes, making communication seamless for both people and machines. As we move forward, you'll see how these foundational ideas set the stage for everything in networking. Now let's dive into addressing. Every device on a network gets a unique internet address made up of 4 bytes separated by periods, like 13610223349. The first part identifies the network while the rest points to the specific device. Assigning these addresses is managed by organizations like Internet, which consider things like geography and organization type. But remembering numbers is tough, so we use the Domain Name System, or DNS. DNS translates easy-to-remember names into those hard numeric addresses. Whenever you type a website name, DNS is working in the background to connect you to the right place. Beyond just identifying devices, networks also need to distinguish between different applications running on the same machine. That's where ports come in. Each application gets a unique port number. Think of it as an apartment number in a building. For example, port 80 is reserved for web traffic HTTP, while port 25 is for email SMTP. There's a huge range of port numbers, allowing many applications to run simultaneously. This system ensures that data gets to the right program, not just the right computer. Modern networks use a method called packet switching to send data. Instead of sending a whole message at once, the data is broken into smaller units called packets. Each packet travels independently across the network and is reassembled at the destination. Every packet contains a header with source and destination addresses, plus sequencing information to help put the message back together. This approach makes data transfer efficient and reliable, even if some packets take different routes to reach the same endpoint. Networks come in different sizes. Local area networks or LANs cover small areas like buildings or campuses. They use technologies like Ethernet Token Ring or FDDI, each with its own way of connecting devices, bus ring or dual ring topologies. Wide area networks or WANs span cities, countries, or even continents using technologies like ATM or ISDN. The speed and design of these networks vary, but together they form the backbone of our connected world. Build larger networks. We connect smaller ones using devices like bridges, routers, gateways, and more. Bridges link similar networks, routers connect different types, and gateways translate between systems. The overall layout or topology of a network includes the physical arrangement of devices and the connections between them. Understanding these elements helps in designing efficient, scalable networks that can handle growing demands and diverse technology. Protocols are the rules that govern how devices communicate over a network. They define the format and meaning of messages, how errors are detected and corrected, and how data is routed. For example, the HTTP protocol manages web traffic, while SMTP handles email. Protocols are often described in documents called RFCs, which set the standards for how communication should work. These rules ensure that devices from different manufacturers can talk to each other smoothly. Manage the complexity of networking. Protocols are organized into layers. The OSI model has 7 layers, from the physical hardware up to the applications we use. Each layer has a specific role, like handling data transmission, managing sessions, or formatting data. The TCP/IP model, which powers the internet, simplifies this into 4 layers: application, transport, internet, and network. Each layer adds or removes headers as data moves through, making communication modular and manageable. At the heart of the internet are protocols like IP, TCP, and UDP. IP handles addressing and routing, breaking data into packets and sending them across networks. TCP ensures reliable delivery, checking for errors and keeping data in order. UDP, on the other hand, is faster but doesn't guarantee delivery, perfect for quick, repetitive tasks. On top of these, application protocols like FTP, Telnet, and SMTP provide services like file transfer, remote access, and email. Together, these protocols make the internet work, connecting people and devices around the globe.